For today's class. Yes, hello everyone. This is lecture 8 on computer networks, and in this lecture, we are going to resume our previous lecture only. So, in the previous lecture, we were discussing go back N protocol. Okay, and one question was left out, and let us do that question also. So, let me tell you the year of the question. Okay, so just a second. I think it's GATE 2015 question. Okay, let me check that out. Yeah, it's GATE 2015. Okay. So let us solve this question. Consider a network connecting two systems located 8,000 kilometers apart. So station 1, station 2. They are 8,000 kilometer apart. Okay, the bandwidth is given as 500 into 10 to the power 6 bps bits per second. Propagation delay. Okay, propagation speed. So speed is given as 4 into 10 to the power 6 meter per second. Okay, so immediately you change the distance as 8 into 10 to the power 6 meters. Are you getting it? 8,000 kilometers, so 8 into 10 power 6 meters. Okay, now it need to design go back N sliding window protocol for this network. The average packet size, so packet size, okay, packet size is 10 to the power 7 bits. Network is to be used to its full capacity. So see, they will try to twist the question as much as possible. So what do you mean by network is to be used to full capacity? That means your efficiency is 100%. Okay. So otherwise they will say that channel is fully packed and so on. That is a different scenario. But here they are saying network is to be used to full capacity. That means efficiency should come out to be 100%. Okay. Assume processing delays at the nodes are negligible. Okay, then the minimum size in bits of sequence number field has to be. So sequence number field minimum bits they want to ask. Okay, so how we will approach this question? That is very easy. So efficiency is 100%. Now the efficiency is what? N upon 1 plus 2a. For go back and we have studied this formula in the previous lecture only. So so efficiency is 100% means 1. So 1 is equal to N upon 1 plus 2a. So N is equal to 1 plus 2a. Okay, so the this is your window size. Okay, or rather we should say center window size. So center window size should be 1 plus 2a, and receiver window size, that is for sure for go back and it is 1 only. Receiver window size will be 1 only. Okay, regardless of anything, go back and means receiver window size 1 and center window size is 1 plus 2a. So now we can calculate 1 plus 2a very easily. So TP upon TT. So 1 plus 2 into TP. What is TP here? Propagation time. They have not mentioned. So distance upon speed. So TP will be equal to distance. Distance is 8 into 10 to the power 6 upon speed 4 into 10 to the power 6. So it comes out to be 2 seconds. Okay. Yeah. So and what about transmission time? Transmission time is message size upon bandwidth. What is the message size? 10 to the power 7 bits. Packet size or message size, one and the same thing. Message upon bandwidth. Bandwidth is 500 into 10 to the power 6. So this comes out to be what will be the value? 10 upon 500. So it comes out to be 1 upon 50, that is 20 milliseconds. Okay, 20 milliseconds. So divide, or you can say 20 into 1000 here. Okay, so I think there is some mistake or everything is fit and fine. Let me check that out. Yeah, everything is fit and fine. I hope so. Okay, so what should be the value here? Upon 20, so 1 plus, yes. So 1 plus 2 into 2 into, yeah, so it comes out to be 401. 401. Okay. Yeah, so I think see this, if some mistake is there.
I think it is 20 we cancelled.
Oh, oops. It comes out to be 1 by 15. So into 1000. Yeah, so it should be 20 millisecond only. Yes, so 20 Okay, so I think what is the
Sir,
mistake here? Small calculation mistake.
denominator 2 will cut 100 also, no, sir.
Ha. Yes,
Yeah,
yes, yes.
it will be
Yes.
round up to 201,
Ha,
sir.
201. 201. Yes.
Yeah,
201
yeah.
is the answer. Yes.
Uh-huh.
So a small mistake. 201 is our answer. Yes. So sender window size is coming to be 201 and receiver window size is 1. So available sequence number, I think you already remember available sequence number. Forget about go back and SR any protocol. Available sequence number should be greater than or equal to sender window size plus receiver window size. We have studied this formula many times. So available sequence number should be greater than or equal to 201 plus 1. That means available sequence number should be greater than or equal to 202. Okay, so number of bits they want to ask. So log base to 202 ceiling function, it comes out to be 8. Okay, I think you have got it. Now 2 power 7 is 128, 2 power 8 is 256. So 8 will be our answer. Ceiling function we have to take, so 8 is our answer. Okay.
Understood, sir. Yes, sir.
Yeah, so take snapshot. I will jump to the next slide, and now we are going to start our next protocol. Go back and is now completed. Now we are going to start the next protocol, that is selective repeat. Take snapshot.
Done, sir.
Okay, so now we are going to start SR protocol, that is selective repeat ARQ. Selective repeat ARQ. ARQ is automatic repeat request. So as the name suggests, selective repeat, that means only those frames will be repeated whose timer expires. Okay, so selectively we have to repeat, but in go back and what we were doing, entire window was retransmitted. For example, window is at, say, window size is 3, we are using GB3. Okay, so if timeout occur for frame number 1, then we will go back and positions and send all the frames in the window. So entire window was retransmitted, but here selective repeat, that means only those frames will be retransmitted whose timer expire. That is the basic meaning of selective repeat. So if you want to write line, then you can write. These notes will help you a lot while revising. So please take the notes. As the name suggests, when timer expires, for a packet, when timer expires for a packet, then only that packet is retransmitted. Then only that packet is retransmitted. But in go back n, entire window of n packets was retransmitted. Okay, but in go back n GBN, entire window of packet is retransmitted. Okay, entire window of packet is retransmitted. Okay, and next important point, since only that frame is retransmitted which whose timer expire and so on, so from that we can guess that out of order delivery is accepted here. Okay, if out of order delivery is not accepted, then obviously if first frame timeout expire, then we have to go back and send all the frames again, like go back and. So out of order delivery should be accepted here, because we have to repeat only that frame whose timer expires. So please write down that point also. So unlike go back and, here out of order delivery is accepted. Unlike go back and, here out of order delivery is accepted. Out of order delivery is accepted. Next point. So second important point was out of order delivery accepted. Okay, now in the first point, which what I have said, that in SR only that frame will be retransmitted whose timer expire. So now I think you remember in go back and timer was maintained for only first frame, but here we have to maintain timer for each and every frame in the window. Okay, so next point, write down timer is maintained for each and every frame in the window. Timer is maintained for each and every frame in the window at center side. Timer is maintained for each and every frame in the window at center side. Okay, so third important point was related to timer. First important point was SR, selective repeat. Okay, selective repeat, I have written it just for the remembering. Selective repeat, selectively it will be repeated, but go back and entire window was repeated. Okay, second was out of order delivery accepted. Third important point was timer is maintained for only for every frame. Okay, timer for every frame. in the window. Timer for every frame. Okay. So now we can think that since out of order delivery is accepted, so obviously receiver window size cannot be 1 na? If receiver window size is only 1, then it will need only 1 frame. So if out of order delivery will come, it will reject, because it will say no, my window is at 1, so I will receive only 1 frame. No doubt it need 2 in the near future, but it will reject it, saying that I need only 1. So here receiver window size should be greater than 1. Are you getting it? So that is here, okay, let me ask this in the form of question, because this question I have been asking it many times. See, write down the question. If m bit overheads are allowed, if m bit overhead is allowed in header of frame, if m bit overhead is allowed in header of frame, if m bit overhead is allowed in header of frame, then what is the maximum size of window? Then what is the maximum size of window at sender and receiver side? Okay, maximum size of window at sender and receiver side. Okay, so to solve this question, we should know that here sender window size and receiver window size both are same. Okay, sender window size SWS, that is equal to receiver window size. Both are of same size. For example, if sender window size is of 5, receiver window size will also be of 5. If sender window size is 3, receiver window size is 3, and so on like this. Okay, so now it is no longer 1. Okay, receiver window size is no longer 1, because if it is 1, then it will be go back n. Now here both will be same. Okay, so now see the question, what it is saying. If m bit overhead are allowed, then maximum size of window at sender and receiver side. So maximum window size, how we will calculate? So we will say the formula, available window size, available sequence number, that should be equal to sender window size plus receiver window size. Okay, so available sequence number, if m bit overhead are allowed, total number of sequence number possible are 2 power m. That is very easy. 3 bit overhead, then 8 and so on. We already know 2 power m available sequence number. So sender window size, receiver window size both are same. So let us say it as 2x. X is equal to 2 power m by 2. That is 2 power m minus 1. 2 power m minus 1. Above it is minus 1. But in what was in go back n? In go back n, if you try to remember, if m bit overhead was allowed, then we will say 2 power m is greater than equal to sender window size plus receiver window size. Sender window size was receiver window size was only 1. So sender window size was what? Sender window size was less than or equal to 2 power m niche minus 1. Okay, but here it is above minus 1. So I should say like this, x should be less than or equal to. Okay, so sender window size was less than or equal to 2 minus 1, and receiver window size was only 1. Okay, but here in selective repeat or SR, sender window size, that is equal to receiver window size, that is equal to 2 power m minus 1. This is very important point, and this question has been asked in GATE many times. Okay, so sender window size, receiver window size both are equal to 2 power m minus 1, but in case of go back n, sender window size is 2 power m minus 1, receiver window size is 1. Any doubt here?
No, sir.
Okay, yeah, so that's it. So I think you have written that point now, more than 1. Receiver window size should be more than 1.
Yes,
Okay,
sir,
because if it is exactly equal to 1, then it will be go back and only. Okay, since out of order delivery is accepted, so receiver window size should be more than 1. Okay,
more than 1. In fact, it is equal to the center window size, no, sir?
Yes, 100%. We will say like this, but roughly, if you say minimum, I will say it should be more than 1. Okay, so let me write that point. Take snapshot. I will jump to the next slide.
Done, sir.
Okay, so next important point is, since out of order delivery is accepted, out of order delivery is accepted, so RWS, receiver window size, that should be greater than 1, strictly greater than 1. Because if it is equal to 1, then obviously how you will accept out of order delivery? Out of order delivery means you are expecting 1, but 2 come and you have to accept the 2. So to accept the 2, your window size should be more than 1. Na? Okay, so since out of order delivery is accepted, so receiver window size should be strictly greater than 1. Any doubt here?
No, sir.
Okay.
This out of order word, sir. Rather would have used like unexpected.
packet. Okay, yeah, you can say like this, unexpected. But if we say unexpected, then actually that will create problem. Like for example, 1 2 3. If window is here at receiver side, unexpected is 4 also, 5 also, but we cannot accept it because they are outside the window. They are also unexpected. Okay, so
So
2
out
and
of
3.
order delivery in the sense like the order, like 1 2 3 is the order.
Ha
Out
ha
of
ha.
that,
So so
unexpected.
1 2 3 is the order. So 2 come first or 3 come first. That is out of order delivery. But
Okay.
unexpected means 4 and 5. They are outside the window, but still they come. Then you have to accept them also.
I
So we.
understood, sir.
Okay, so since out of order delivery is accepted, so receiver window size should be strictly greater than 1. Okay. Hmm. So another important point is, since we are saying that out of order delivery is accepted, like for example, window was here 1 2 3, 2 frame number 2 comes first, so you will accept it. Okay. Now similarly, frame number 3 comes, you will accept it. So now question arises whether you can deliver these frames to network layer or not. This is data link layer. No, we will not deliver it. So data link layer will deliver to network layer in order delivery only. Okay, out of order delivery may be accepted, but that delivery will not be transferred to network layer, because ultimately data link layer is just a layer. It is simply accepting the frames. So these frames should be given to network layer. So these frames will be delivered to network layer. They cannot be delivered to network layer out of order, because network layer does not know what is frame number 1 2 3 and so on. So network layer want in sequence only. Okay, so frames might be accepted out of order, but they will be delivered to network layer in order only. Okay, that is very important point. So please write down this point. Out of order delivery is accepted by receiver. Out of order delivery is accepted by receiver, but packets are delivered to upper layer in order. Out of order delivery is accepted by receiver, but packets are delivered to upper layer in order. In order. Okay, out of order is not accepted by network layer. Okay, next. So now since you have to deliver them in order, so directly and indirectly this means that when 1 2 and 3 all the frames will be received by a receiver, only then it will be transferred to network layer. So now if 2 comes first, then 2 will be before 1. Okay, and then 3 comes like this, so frames will be like this. So now these cannot be transferred to network layer na? So you have to sort them 1 2 3, and then you can deliver to network layer. So another big difference is coming with SR and GBN. In GBN there was no sorting because out of order delivery was not accepted. So now here, since it is accepted, so you have to do sorting also, and where sorting will be done? At receiver side. Okay, so at receiver side sorting must be done, and then after sorting these frames should be delivered to network layer. Okay, but it was not there in go back n, because in go back n window size was only 1. There was no out of order delivery. So I think you have heard the very famous saying, there is never a free lunch. If somebody is providing you lunch, then there is some hidden meaning. So here also that is the problem. So this out of order delivery is not free. You have to bear some cost. The simplest, or you can say the biggest cost is this window size. Okay, that means you have, window means buffer, so you have to maintain buffer of big size at receiver side, because in go back and only one was there, but here we have to maintain big size. Second thing, sorting should be done. Okay, so CPU time is needed. Okay, so it is not free, so you have to bear the cost of it. So we have written like out of order delivery is accepted by receiver, but packets are delivered to upper layer in order. Hence sorting of packets is done at receiver side. Hence sorting of packet is done at receiver side.
Yes, sir. I made a
Okay,
point of it.
yeah. Okay, next important point. So for example, see this 1 2 3 4 5 and so on. Like this 1 2 3 is this is your sender side and this is your receiver side. Okay, so this is sender and this is receiver side. So now sender has sent 1 2 3 all the frames. Now if by chance 2 comes first, okay, 1 has not come, so receiver will send negative acknowledgement, NAK concept was not there in go back n, but in selective repeat we have concept of NAK, that is negative acknowledgement. Negative acknowledgement means NAK1 means receiver will say to sender that I was expecting 1 but 2 has come first, so please send me frame number 1 as fast as possible so that I can deliver these 1 and 2 frames to the network layer. Okay, so but the condition is that this NAK will be sent only for the leftmost frame in the window. It will not be sent for other frames. Okay, for example, if we have say window sizes 1, 2, 3, 4, and 5. 5 frames are there in the window. Now, for example, if frame number 3 comes first, you will say NAK1, NAK1. Okay, now if now frame number 1 come into the picture. Okay, and now frame number 5 come into the picture, so you will say no, I was expecting to, please send me to, and so no, it is not like that. Okay, so NAK is sent for only first frame or only leftmost frame in the window. Okay, it is not sent for other frames. Why? Just because the moment sender receives this NAK, it will immediately send the frame number 1 again. It hardly matters that its timer expired or not. I have told you, na, timer is maintained for each and every frame in the window. Now, if frame number 1 will be retransmitted when it timer expire. But if NAK is accepted by a sender, because NAK is sent by receiver, then it will not check its timer. For example, its timer was for 1 hour. Now it will not wait for 1 hour. It will immediately send the frame again.
Yes.
Okay, so now imagine if for each and every out of order delivery NAK is sent, then obviously it will create problem. Sender will keep on sending the other frames. It might be the case that they arrive just after few seconds, so you have not waited for few seconds, so you will immediately keep on transferring. That will create problem. So patience is very must. Okay, so we have to get good efficiency also. Why you want again and again retransmissions? So that is the reason that NAK is sent for only first frame, or you can say only leftmost frame in the window. Okay, yeah, so please write the point.
Sir.
Okay, so NAK is sent for first out of order delivery. For first out of order delivery, NAK is sent. Okay. Next point. When NAK is received by sender, who will receive it? Sender will receive it, na? And who is sending NAK? Receiver is sending NAK. So that's why I'm writing when NAK is received by sender. When NAK is received by sender, then what it will do? So, for example, it has sent lots and lots of packets, and for every packet, it is maintaining timer. Okay, so now, for example, if NAK1 come, then sender will have to search its window, and it has to find frame number 1, and it will retransmit it. So again, searching is needed. So at receiver side, sorting is needed. At sender side, searching is needed, and they were not needed in go backend. Okay, so for out of order delivery, you have to do lots and lots of different tasks. Okay, yeah, so please write down the point. So what we have written, so when sender receives NAK, when sender receives NAK, then it will search its window, and immediately send the respective packet. It will search the window and immediately send the respective packet regardless of its timer. Immediately send the respective packet regardless of the timer. Okay, it hardly matters timer expired or not, you will send it again. Okay, regardless of the timer. Okay, and last important point is coming. Since timer is maintained, okay, take snapshot. I will jump to the next slide.
Done, sir.
Okay, so now I have told you that in window we have say frame number 1, 2, 3, 4, and 5. So timer is maintained for each and every frame in the window, na? And whose timer expire, only that frame will be sent again. So obviously, when sender has sent these frames, receiver have to send the acknowledgements. All these, so since these frames are sent individually, because for each and every frame we have maintained timer, so these must be acknowledged individually. So in GBN, what we were saying, acknowledgements are cumulative. Cumulative in the sense for each and every, so for example, all the frames are received in sequence, then a receiver was sending only one acknowledgement, and this acknowledgement represent acknowledgement for all the frames. So in place of sending individual acknowledgements, we were using cumulative acknowledgement. But here, since timer is maintained for each and every frame, so each and every frame must be individually acknowledged. Okay, so we are not using cumulative acknowledgements here. So write down this point. Unlike GBN, here acknowledgements are independent. Unlike GBN, here acknowledgements are independent. Unlike GBN, here acknowledgements are independent. Bracket में please write in bracket non-cumulative. Independent means non-cumulative. Non-cumulative. That means every packet is acknowledged by receiver. That means every packet is acknowledged by receiver. Okay, every packet is acknowledged by receiver. Okay. Okay. So next is efficiency. Now this is all about your basic terminologies and all. Now we will study efficiency. I'm jumping to the next slide now. So efficiency of SR. Efficiency of SR. So see this. I will say if m-bit overheads is allowed. If m-bit overhead is allowed in frame header, then what can be the maximum, you can say maximum window size? That was 2 power m minus 1. We have just solved it. Okay, and what is the efficiency? N upon 1 plus 2a. 1 plus 2 is the maximum number of frames which we can send, and n is the frame which we are sending. So it will be 2 power m minus 1 upon 1 plus 2a. That is the maximum efficiency which we can achieve. Okay. Yeah, but in SR, in go back n, it was 2 power m minus 1 upon 1 plus 2a. This is for GBN. This is for GBN, and this is for your SR. Okay. So you can take the snapshot. I will jump to the next slide now. Done?
Yes, sir.
Okay, so now we will make a summary. Okay, that will clear each and everything. So here I will write properties, and here we will write stop and wait, go back n, and SR. Okay, so first property is sender window size. Sender window size. In stop and wait, only 1. In go back n, it can be n. In SR also, it can be n. Okay, and receiver window size. In stop and wait, only 1. Go back n, only 1. But SR, n. Because sender and receiver window size are same. Okay, so sequence number. So available sequence. Yeah, come again.
In stop and wait, it was 1, sir.
Sender window size and receiver window size both are 1, na? Because sender was sending only 1 frame, and then it stop and wait for acknowledgement from receiver.
Yes, sir. Yes, sir.
1 and 1 only. So available sequence number. So available sequence number, I think I have told you, available sequence number should be greater than or equal to sender window size plus receiver window size. Okay, so available sequence number needed only 2. 1 plus 1. Here n plus 1, and here 2n. Okay. Yes. Next is efficiency. Efficiency is 1 upon 1 plus 2a. Maximums which we can send 1 plus 2a. But in stop and wait, we are sending only 1 frame. So 1 upon 1 plus 2a. Here n upon 1 plus 2a. And here also n upon 1 plus 2a. Because we are assuming in go back n we are sending n frames and waiting for acknowledgement. In SR also we are taking n only. Okay, but in GBN and SR, sender window size is roughly we are taking as same, but receiver window size is different. In it is 1, and here it is n. Are you getting it?
Yes, sir.
Okay, so next, so roughly we can say that efficiency is same. Okay, but actually efficiency, see, we are saying that GBN, mathematically we are saying GBN and SR efficiency is same, but actually SR will be much more efficient. Why? Because selective repeat, na? We will repeat only those frames which are not been you can say whose timer expire. But in GBN, if timer expire for the first frame, we have to repeat entire window. That is the problem. Okay, next ACK. Acknowledgements. So here obviously acknowledgement is individual. There is no cumulative kind of thing because top and wait only one frame is sent and it is acknowledged and so on. It is very very simple individual acknowledgement. But here it is cumulative. We have told you it was cumulative, and here individual. Okay. Yeah. Next is out of order delivery.
We have
Okay.
negative
So
acknowledgement as well.
yeah, we have negative. I will write that point also. Okay.
Uh-huh.
So out of order delivery. Out of order. Not allowed. Not allowed. But it is allowed. Okay. Yeah. Next, NAK. Here no NAK. No NAK concept. Here NAK concept is there. Okay. So next is number of retransmissions if packet is lost. Let me write it with red color. It is very very important point. Number of retransmission if packet is lost. Only one, because only one frame was sent. If that is lost, you will send it again. But in go back and N, if one frame lost, that will be the leftmost frame in the window, and you have to repeat entire window. We have solved numericals also in the previous lecture. In SR, only one. That is the basic meaning of SR, the selective repeat. Okay. So CPU requirement here. Obviously it is low. Here it is low. Here it is high. Why? Because we need sorting also at receiver side, and we need searching also at sender side. Sorting at receiver and searching at sender. So CPU requirement is high. Okay, these are the basic differences between stop and wait, go back and SR. Okay, this summary is very very important. Yes, any doubt here?
No, sir.
Okay, take snapshot. I will jump to the next slide.
Done, sir.
Okay, so just as we have done these types of question in SR also, in go back and also, let me tell you that type of question. So if sender wants to send 10 frames, I am writing roughly frames. The number of frames we want to send is 10, and every fifth frame is lost. Every fifth frame lost. Okay, so total number of frames sent. Total number of frames sent in SR. So in SR, what we will say 1, 2, 3, 4, 5. This is lost. So again repeat it. I have told you selective repeat. That means this is the beauty, na? Only that frame will be retransmitted whose timer expire or who's lost. So 1, 2, 3, 4, 5. Then again 5 is repeated. Then 6, 7, 8, 9. 1, 2, 3, 4, and 5. This is fifth frame. Are you getting it? You have to count from here. 1, 2, 3, 4, 5. Fifth frame is lost. So you will repeat 9 and then 10. So 1 and 2. Okay, so we have not reached till fifth, so no problem. So how many retransmissions are there? 2. Total frames were 10. So 10 plus 2, that is 12 is the answer. So simple. Okay, now same answer, this is for SR also, and this is for stop and wait also. But for go back and we have done this in the previous lecture. Okay, so we are not going into details and so on. For go back and we have to see first the window size. Okay, if window size is 4, window size is 3, try to remember. We have solved these types of question in the previous lecture only. Okay, so yeah, you can take the snapshot. So for stop and wait also same scenario. We have studied this. For SR also same scenario. Okay, yeah. So you can take the snapshot, and I will jump to the next slide. Okay. So next is a gate question. Let me see where is that question. So this is this comes in, I think, gate 2016. So what they are saying is consider a 128 into 10 power 3 bits per second satellite communication link. So bandwidth given to us as 128 into 10 to the power 3 bits per second with one-way propagation delay of 150 milliseconds. So TP, one-way means only TP. Round trip time means 2 into TP is given. 150 millisecond. Selective repeat protocol is used, SR. Okay, so question is of SR. On this link to send data with a frame size of 1 kilobyte. Okay, so frame size is this is in bits per second, so immediately convert 8000 bits. Okay. Neglect the transmission time of acknowledgement. Minimum number of bits required for the sequence number field to achieve 100% utilization. So number of bits required. Okay, so I think we have solved many type of question like this only. Sequence number field to achieve 100% utilization. So efficiency is 100%. N upon 1 plus 2a. So 1 is equal to n upon 1 plus 2a. So n comes out to be 1 plus 2a. Okay, yes, so now we will solve it. 1 plus 2 into a is what? TP upon tt. So a is TP. Propagation time is 150 millisecond, na? So into 10 power minus 3. Okay, and what about tt time? Transmission time, message size upon bandwidth. Message size is 8000 bits divided by bandwidth, 128 into 10 power 3. Okay, yeah, and see this sometimes see, it entirely depends on question to question. We are taking frame size as 1 kilobyte, so 1 kilobyte you can take it as 1000 byte,
Yes.
or you can take it as 1024 byte. Exact answer is 1024. Okay, so it's my suggestion that frame size it's in computer, na. So for
Yes, sir.
computer you will take power of 2 only. For bandwidth etc you can take 1000. Okay, for example, if they say 128 kbps, kilobits per second, 128 kbps, then you will say 128 into 10 power 3. Are you getting it?
Yes.
128 into 10 power 3 you will take. Okay, but if they are saying for data, or they are talking about computer, for that you will take, if they say 128 kilobyte kb data or kilobit data,
Yes.
kilobit data, then you will say 128 into 1024.
Hmm.
Like this you have to take. So here we will take that. So 1 kilobyte frame size, na, so you will take 8 into 128. Okay, sorry, 1024, na, sorry for that. 1024, 1024. Yeah, so now we will try to solve it. So 8 into 2 power 10, 1024 is 2 power 10, 2 power 7 into 10 to the power 3. So if we convert it into power of 2, that will be very easy for us, na. So it will be 2 power 3. So 8 into 8, 64. So 64 millisecond. Is it okay?
Yes, sir. Yes, sir.
So 64 millisecond. So finally, what we will say, your transmission time is 64 millisecond. So I will divide it by 64. Yes, so 1 plus 2 into 64 divided by 120. Now this is very, very important. Millisecond was there, na, so into 10 power minus 3. So it will go down and so on. So now what should we take? 64 in 150 upon 64. 2 point something it will come. Are you getting it? So we have to take, now this is window size, na. We cannot take in point. Are you getting it? We cannot take it in point. So n should be is equal to 1 plus 2a. So you will take either 2 or 3. Okay, so we have two choices now left. We can take n is equal to either 2 or 3. So you will take either 2 or 3. So if you take 2, you will get 5 as the answer. If you take 3, you will get 6 as the answer. Okay, so now actually it hardly matters. See this is the beauty of the GATE exam. Now they will make question in such a way that there should be no ambiguity in anybody's mind. If you take n to be 5, that means sender window size is 5, and we know available sequence number is greater than or equal to sender window size plus receiver window size. Okay, so available sequence number, so sender window size is 5, receiver window size is also 5, so that should be greater than or equal to available sequence number. So available sequence number should be greater than or equal to 10. So minimum number of bits required will be log base 210 ceiling function. So for 10 we need 4 bits. But if we take 6, then what will be your answer? Available sequence number should be greater than or equal to 6 plus 6. So available sequence number should be greater than or equal to 12. So log base 212 ceiling function, it comes out to be 4 only. Are you getting it now? So both are giving us 4, no problem at all. So answer is 4, that is for sure. Now question arises, if we want to dig deep into the concepts, what should be your exact answer? If by chance they give you number of, they do not want minimum number of bits, they want window size only, then what should be your answer, 5 or 6? So we have to check that out. Okay, so we will try to do the reverse procedure for it, and we will try to find out what should be your exact answer, 5 or 6. Okay, so assume if you take 5, then you are sending 5 frames. See, 100% efficiency means sender should never remain idle. Okay, let me write it. Okay, so let me do it on the next slide. Take snapshot. It will become messy. Take snapshot. Done. Okay, so now what do you mean by 100% efficiency? 100% efficiency means sender should never remain idle. Sender should never remain idle. Okay, if sender is idle, then obviously it is not 100% efficiency, no? So now you have to check, that means sender should always be busy. So now you have to check whether it will remain busy for 5 or it will remain busy for 6. So if you are sending 5 frames, what is the transmission time for one frame? 64 millisecond. Now if you are sending 5 frames, so 64 into 5, what it comes out to be? 5 4s are 20, 6 5 are 30, 32, 320 millisecond. Okay, and what is this? So total time, I think you already remember. So in previous lecture we have solved sender and receiver, frame was sent and its acknowledgement came. So what was this time? TT plus 2 TP, na? Are you getting it? TT plus 2 TP was the total time.
Yes,
So so this time should be less than 320, na? Okay, so if this time is more than 320, then obviously I will say for some amount of time sender has remained idle. If sender has remained idle, then how you will get 100% efficiency? That is the problem. So now please see this. Transmission time was 64 millisecond. See this. Transmission time was 64 millisecond and propagation time was 150, na? So 300. 64 plus 2 TP, na? TP was 150, so it will be 300. So 364. So 44 millisecond you have remained idle. So it is not good. Okay, so 5 should not be the answer. If we take 6 as the answer, then what should we do? 64 into 6, it comes out to be 6 for the 24, 336, 384. So 384 millisecond time it will be busy. For 384 millisecond it will be busy, and TT plus 2 TP is coming to be 364. So obviously you remain busy. So now we can say that till 5 frames you have transmitted properly, and 6th frame you were transmitting, and at that time acknowledgement for the first frame come into the picture. So you have transmitted half or like that 6th frame, and still your acknowledgement come. So that means sender is still busy. Are you getting it now? So 6 should be the best answer. 5 should not be the answer, 6 should be the answer. Okay, so now we are ahead of your GATE exam. Ahead in the sense they have asked this question, so 5 or 6. So in many solutions online and many cases you will see like this also it hardly matters 5 or 6. You will take only 4 bits, so 4 is the answer. Okay, but we have clearly you can say clarified what should be your exact answer, 5 or 6. Okay, yeah, so I hope it's clear to everybody. Please take snapshot of this slide also, and then we will jump to the next slide. Okay, and now here we have completed your you can say first part of protocols for the data link layer. Now we are jumping to the second part of the protocols. Okay, so let me tell you that also. Take snapshot. I will jump to the next slide.
Yes, sir.
Okay, so the next is your see, actually data link layer is divided into 2 sub layers. Okay, so below data link layer is physical layer, and above it is network layer. Okay, so this data link layer is divided into 2 parts. So below part is known as MAC or media access control, and above part that is known as LLC or logical link control. This division was done by IEEE, Institutes of Electrical and Electronic Engineering, IEEE. Okay, IEEE papers are very prestigious if you do research in IITs and all. So many students prefer to publish paper in IEEE. Okay, if your papers are published in IEEE, then you are eligible for research in higher universities like in US, Canada, and so on. You can do like research in these universities if you have at least 1 or 2 publications in IEEE. So it is very prestigious organization, and this organization has divided this data link layer into two parts: LLC and MAC. LLC is logical link control. LLC is logical link control, and MAC is media access control. MAC is media access control. Okay, LLC is logical link control, MAC is media access control. Okay, so this above layer LLC work we have done. What was its work? Framing. Next was flow control, and next was error control. We have studied all this. So flow control and error control, we have studied stop and wait, go back, and SR. We have completed all this. Okay, so directly indirectly I want to say LLC work is over. So if you say me that what is the exact work of LLC, I will say LLC will handle all the issues related to node delivery. The only thing is you should have a dedicated link, like this is sender and this is say router, this is router and this is receiver. So all the issues related to node delivery, this can be handled by LLC, logical link control. Okay, so whether it is framing, flow control, error control, everything will be handled, no problem. Then this is MAC. MAC is media access control, as the name says, media access control. Okay, so media should be accessed properly. For example, so if this media if we have a dedicated link here, then no need to worry about it. Okay, so who will access the channel when it hardly matters to me, na? So and anybody can access because we have a dedicated link, so no problem at all. Now here there is no use of MAC layer. MAC layer is not needed because we have a dedicated link. But MAC layer will come into the picture when we have a shared media. Okay, so for example, let me jump to the next slide and tell you the things. Take snapshot.
Done, sir.
Okay, so see this. For example, we have station A, B, C, and D. Okay, this is station A, this is station B, this is C, and this is D. Okay, so total we have say 4 stations. Now when B and C are communicating, then A and D cannot communicate. Okay, for example, when B and C are communicating, then A and D cannot communicate. Why? Because they have to access this shared channel. Okay, so obviously they cannot communicate because data will collide and so on, collision will occur. Okay, so now this question arises, who will access this shared channel when? Now MAC layer will come into the picture. Okay, media access control, that means who can access the shared channel when. Okay, there are multiple stations and they should access the channel in such a way that collision should never occur. Okay, collision should not occur and everybody should get its turn. It is not like that when A and say B and C keep on communicating, A and D will never get its turn and so on. It is not like that. Okay, so responsibility of MAC is that no collision should not occur, and second is everybody should get its turn. Okay, every station get its turn. Every station get its turn. If every station is not getting that done, then what is the use of this layer? Okay, so that's it. Directly indirectly there should be no starvation. Don't worry, starvation and all we will study that in your operating system. Okay, starvation means never getting the term. Okay, there should be no starvation and there should be no collision. These are the two basic responsibilities of MAC sublayer or media access control. So take snapshot. I will jump to the next slide. I hope everything is fit and fine.
Done, sir.
Okay, so now we are going to study the protocols. Okay, so media access control, again and again I'm repeating, if sender and receiver are connected by a dedicated link, there is no need of MAC. MAC will come into the picture when we have shared channel. Okay, let me write that point also, that is very important. Okay, so if we for dedicated link, MAC is not needed. For dedicated link, MAC not needed. I think you have heard the word MAC address. Okay, physical address is also known as MAC address. MAC address just because of this media access control layer. Okay, so take snapshot. I will jump to the next slide and now we will start the protocols.
Done, sir.
Okay, so now see the protocols. So broadly we have three categories of protocol. I think I'm writing something. Is it visible?
The screen share is lost, sir.
I have got this sound. The sound is it's just like it's okay. So yes, now I'm writing something.
Yes, sir. Yes, sir.
Okay. So now we are going to study MAC protocols. Okay. So media access control protocols. So broadly, if we see, there are three categories of protocols. Okay. So let me show you these protocols. Yes, just a second. So first is random access. There are three categories of protocols: random access. Next is control access, and next is uh, channelization protocol. Okay, channelization protocols. So random access protocol, they are very important, and many times question have been asked from these protocols. So what are the random access protocols? The very first is pure aloha. Next is slotted aloha. Next is CSMA, CSMA CD, and CSMA CA. Okay, so basically we have only two protocols, Aloha and CSMA. This Aloha is of two types. Okay, Aloha is of two types, pure Aloha and slotted Aloha. And CSMA, actually CSMA is one protocol and it has two extensions, CSMA CD and CSMA CA. Okay, so these are the two extensions of CSMA. Actual protocol is CSMA. So we have only two protocols, Aloha and CSMA. Aloha is of two types, pure and slotted, and CSMA extensions are, there are two extensions of CSMA, CD and CA. CD is collision detection, CA is collision avoidance. Don't worry, we will study that. Don't worry. Okay. Next is controlled access. For controlled access, you should know the names only because they are not in your gate syllabus. Reservation, polling, and token passing. Okay, so earlier it was there, token passing, token ring, LAN we have to study. So token ring was very important topic for in I think till 2020 it was there. After 2020 this token passing has been removed. Okay, so no need to worry. Or I think it was, I think 2018. Oh, okay, whatever may was the year, after say 2-3 years back, this topic has been removed from gate exam. Okay, but previously it was there, so don't worry, they will not ask question from this topic, don't worry. Okay, last is channelization. Channelization is FDMA, TDMA, and CDMA. Okay, so reservation, polling, and token passing, and this is FDMA, TDMA, CDMA. So they are not in gate syllabus, so no need to worry. If you want me, then I can just give you a full form. FDMA is frequency division multiple access. FDMA is frequency division multiple access. TDMA is time division multiple access. Time division multiple access. CDMA is code division multiple access. Code division multiple access. CDMA phones, they were coming, I think,
Yes.
10 years down the line. Code division multiple access. CDMA. Okay. Yes. And reservation, polling, and token passing, they are not in syllabus. But if you want me one line, then I can say reservation means if station want to send data, then it will do reservation of the slot. Like you travel in a train, then before traveling you do reservation so that your berth is reserved and you will go and sit on that berth. That is the scenario here. Okay, so in reservation, every station actually every station will do reservation, and according to the time slot given, that station will send the frame. or that station will send the data. Only one line I am saying. It is not in gate syllabus, just to give you idea. Okay, so reservation, as the name suggests, if early in early stages, station will do reservations. Okay, and time slot will be given to them, and in that time slot they will send the data. Okay, so in that time slot only one station will send the data, because only one frame, or sorry, only one station has done the reservation, no? Okay, that is the reservation. Next is polling. Polling means, like, for example, I am in a class and I say question to somebody, or rather I ask question. So now students will raise their hand and say, I will answer, I will answer. That is just like polling. Polling means asking. Okay, we do polling now in day-to-day life. That is polling technique. That means we have a, say for example, you can say we have a, like, actually it is used in wireless LANs, WLAN. So you have wireless router in your home. Okay, so that router, like this is a router at your home. Okay, so now this polling technique is used by this router. So you might say, sir, we have only one IP address. Okay, because if you are connected to internet, or your ISP has provided, internet service provider has provided only one IP address to your router. Okay, that IP address is given to your router. Now with only one IP address, we can use only one computer or one PC. But what we are doing, we are connecting, say, 3-4 laptops, one PC, 2-3 mobiles. How these all systems are communicating with only one IP address? Okay, that is done with the help of polling only. Okay, so what we will say, so say for example, we have 4 devices. So this WLAN router, it will ask first this: do you want to send data? He will say no. Then it will ask him, do you want to send data? He will say no. It will say, ask him, do you want to send data? It will say yes. He will send the data, and now it will send to the internet, and so on, like this. That is polling. Okay, so this router is doing polling now. This is saying to this, do you want to send data, do you want to send data, and so on. I'm not going into detail because it is not in gate syllabus. I'm just giving you the idea. Okay, yes, token passing, that is very easy. I think you already know the whatever station is having token, only that station can send the data. Okay, so for example, we have a ring topology. Okay, so token is a special frame which keep on rotating in the network. So now, so for example, this is a token. Okay, so this is a token. Now this token comes to this station. If this station want to send data, it will absorb this token and send the data. Okay, and if it does not want to send data, it will release the token, and releasing token means it will send it. This token is a special frame. Okay, it is of 3 byte and so on. I'm not going into the details. So this token will be sent on to this, it will release the token means this station will send this 3 byte data to this channel. Now this station will receive, if it want to send data, okay, otherwise it will release the token, and so on. Token will keep on rotating in this network, and whosoever want to send data, he or she, or that station will absorb the frame, absorb this token frame, and send the data. Like that, we have to do the things. Okay, so the basic thing is, token is a special frame which keep on rotating in the network, and whosoever station wants to send data, that station will absorb the token and send the data. That's it. So that if station is having token, or the station having token, that is authorized to send the data. Other stations cannot send the data. Okay, yeah, and then there are many scenarios, like what if token is lost, how many frames can be transmitted, what is the size of the frame, and so on. We are not covering that because it is not in gate syllabus. I have just given you small hint of it. That's it. Okay, and forget about these are very lengthier techniques. We cannot understand them in 2 to 3 minutes, so I am leaving them. It is not required, forget, don't worry. These are very, very important. Okay, random access protocols are very, very important. Okay, so we will study them. Okay, so first of all, let me say like this: control access. So everything was controlled by somebody. Okay, like reservation. Every station was doing reservation, and then they were sending polling. Polling is controlled by this centralized station or router. He is asking everybody. Okay, in token passing, token was there. So whosoever station was having token, that can send the data, and so on. There was some controlling authority. Random access, as the name suggests, it is completely random. That means the no station is superior to somebody, no station is inferior to somebody. Like there is no boss and employee relationship. Like boss is somebody who will instruct everybody and so on. There is nothing like that. Everybody is colleagues, or everybody is like just like peers. Peers like your colleagues. Okay, like everybody is having same standards. So directly indirectly, I want to say in random access, no station allows or no station stops any other station to send data. That is the basic meaning of random access. Okay, please write down these points. These are very important. First point: no station is superior to another, just like boss and employee. No station is superior to another. No station is superior to another, and none is assigned the control over the other. And none is assigned the control over the other. No station is superior to another, and none is assigned the control over the other.
Yes.
Okay? That is, no station permits or stops other station to send data. That is, no station permits or stops other station to send data. Okay, no station permits or stop other station to send data. That is, nobody is giving permission and nobody is stopping somebody to send the data. Whosoever wants to send data, that can send the data. Okay, next point. This means station can send data whenever it wants, because nobody is controlling now. So whenever station want to send data, it can send. That is the basic meaning. This means station can send data whenever it wants. Station can send data whenever it wants. Okay, so now imagine a scenario. Take snapshot. I will jump to the next slide. Okay, so now imagine we have a bus topology and there are many stations connected. I have told you no station is superior, no station is inferior. Whenever station want to send data, it can send. So for example, this station A and station B, they want to send data. Want means what? They have some data and they want to send it. Okay, so obviously they will send at the same time because nobody is stopping them to send the data. So obviously at this media, collision will occur. Why? Because data means what? Signal. Signal means current. So current will flow this way also, this way also. Okay, for A. For B also, this the same scenario. It will flow everywhere. Okay, so obviously collision will occur. That is for sure. Okay, so hence collision chances are very high. Please write down this point. What we have written, this means station can send data whenever it wants. So after that you write, hence collision chances are very high. Hence collision chances are very high. Collision chances are very high. Okay, so what should be done now? Since collision chances are very high, so we should say that station should not send data immediately. Okay, whenever it wants to send data, it should not send it immediately. Rather, it should execute some procedure or condition, and when that condition is satisfied, only then it should be allowed to transmit the data. Otherwise it cannot send. Are you getting it? So there should be some procedure or there should be some condition which should be fulfilled. Okay, yeah. Next point, to avoid collision, station must send data. To avoid collision, station must send data by executing a procedure or condition. To avoid collision, station must send data by executing a procedure or condition defined by the protocol. To avoid collision, station must send data by executing a procedure or condition defined by the protocol. Defined by the protocol. Now see this. So now basically the bottom line is, whenever station want to send data, it can send, but it has to execute some condition or something like that. Okay, now see this. Since there is no fixed order, for example, these are A, B, C and D. There are 4 stations. There is no fixed order now, like first A will send, then B will send, then C, then D. There is no fixed order like that. Whenever station want to send data, it can send. So that's why they are known as random access. Okay, random access means randomly they are executing. There is no fixed order in which station will send the data. Okay, please write down this point. Because there is no fixed order in which station send data. Because there is no fixed order in which station send data. Because there is no fixed order in which station send data. So these are called as random access protocol. So these are called as random access protocol. Okay, that means they will access the channel randomly. That's it. Simply we can say they can access the channel randomly. Okay. So we should say they can access the shared channel randomly because channel is shared, na? It is not their individual piece of property. Okay, they can access the shared channel whenever they want. Okay, next. Now, since because of this random access, every station is competing. There is a kind of competition. Now, for example, gate exam is completely random access. Whoever wants to give gate, he or she can give it. Okay, he can fill the form and he can give the exam. There is no fixed criteria like you have to do like this, you have to do like this. That is not the case. Okay, so everybody can fill and everybody can compete. Okay, so there is a sense of competition, na? Like A, B, C, and D all want to send data at the same time. Okay, so they will do competition and all. That's why we call these method as contention method. Contention means competition. Okay, please write it. Each station compete for the channel. Each station competes for the channel. Each station competes for the channel. Hence, these are also known as contention method. Hence, these are also known as contention method. Okay. So that's it. This is all about introduction to random access protocols. Now see the first protocol which we are going to study, that is pure Aloha. So let me start that protocol. Okay, take the snapshot of this. I will jump to the next slide.
That's
Okay. So now we are going to start the first protocol, that is Aloha. So few basic points about it. We call it as pure Aloha or original Aloha. Pure or original Aloha. Okay. It was developed in University of Hawaii. It was developed in University of Hawaii in 1970s. It was very old protocol. In 1970s it was developed. Okay, and it was originally developed for wireless LANs. It was originally developed for wireless LANs, but it can be used with any media. Okay, but can be used with any type of media. But can be used with any type of media. Okay, originally developed for wireless LAN. Originally for wireless LANs, but can be used with any type of media. Okay. Next important point is each station send equal size frame and this size depends on bandwidth available. So very important point is coming now. Equal size frame. Please write the point. Each station send equal size frame. Each station send equal size frame and this size depends on bandwidth available. Okay, each station send equal size frame and this size depends on bandwidth available. Okay, so you cannot say like one station is sending 100 bytes frame, another station is sending 1000 byte frames. No, each and every station will send equal size frames. Okay, and this size depends on bandwidth available. Okay, next important point is, see, whenever station wants to send data, then it can send it onto the channel. I have told you in random access protocols only, I have told you na in starting that whenever station want to send data, it can send it. Okay, but collision chances are very high, so they have to execute some procedure or some condition, only then it can send the data. Okay, so pure Aloha is saying exactly the same thing, that whenever station want to send data, it can send it onto the channel. That is, there is no fixed procedure. This is very important. I have told you, since collision chances are very high, so station must do some procedure or some calculations or some conditions should be there, and when that condition is satisfied, only then stations will send the data. Okay, but here there is no such condition. Okay, so whenever station want to send data, it can send it onto the channel. So obviously collision chances are very high. Okay, please write down this point. Whenever station has data to send, it can send it onto the channel. Whenever station has data to send, it can send it onto the channel. That is, there is no fixed rule or procedure which will tell about when to send the data.
oh.
There is no fixed rule.
Whenever station has data to send.
Whenever station has data to send, it can send it onto channel. It can send it onto channel. That is, there is no fixed rule. It can send it onto channel. That is, there is no fixed rule or procedure. There is no fixed rule or procedure which will tell about when to send data. When to send data. So there is no fixed rule. So it's as simple as that. See this. Okay, I will first tell you the analogy. Okay, and then I will start this protocol so that you get more clarity. So what Aloha is saying? Aloha is saying, like for example, this is a highway and you are on a service lane, and you want to take your car onto this highway. So what Aloha is saying, you do it blindly. Okay, so whatever will be done, that is that is your fate or your luck. You will do it blindly. Aloha is saying like that. So that is, there is no fixed procedure. Whenever you want, that means you are on a service lane, you want to bring your car onto the highway, you want now, you will do it now only. You will not see, you will not do anything, you simply put your car onto the highway. That's it. This is Aloha. That is pure Aloha, and that is clearly foolish kind of thing. We should not do like that, but pure Aloha is saying like that only. Next we will study slotted Aloha. So what slotted Aloha is saying? Slotted Aloha is saying that you will see the time in your watch. Okay, so you will have a slot of say 1 second, 2 second, or 5 second, whatever may be the case. As the name says, slotted Aloha means time slots you have. Okay, so for example, 10 to 11, this is one slot. 11 to 12, it is another slot. Like you are taking 1 hour slot. Okay, so now if in your mind you think that I will at 10:30, it's come to your mind that I will put my car from service lane to my highway. At 10:30 it comes to your mind. You will keep on seeing your clock. You will not see here and there, you will keep on seeing your clock. Okay, the moment 11 a.m. comes, you will put your car onto the highway, and it's your fate, it's your luck whether you are able to survive or you are not able to survive. It's entirely depends on your luck. That is slotted Aloha. Again, I'm repeating what Aloha is saying. It is a patience less kid. Aloha is, it is not having any kind of patience. The moment you want, you will do it. That's it. That is Aloha. Slotted Aloha, it is time bound. Everything is time bound. Okay, so 10:30 you, it's come to your mind, you will not do that, you will do at 11 o'clock. Okay, like there are many, persons in India, there are many superstitious person in India, like I think you have seen in many movies and all. Plate is there on the table, everything is there. Okay, chapati and everything is there. He is ready to take the breakfast, but he will first do a phone call to a pandit ji that is it the right time to take the dinner. He will say yes, he will take it, otherwise he will keep on watching the clock. That is just like slotted Aloha kind of thing. Superstitious person. Just at fixed time you will do the things. That's it. Next is CSMA. CSMA is very beautiful protocol. That is completely meaningful. You will think CSMA is carrier sense multiple access. You will sense the channel and then you will transmit. That means if you want to take your car from service lane to highway, you will see left and right. If no car is coming, that means you are sensing the highway, and if there is no car is coming, then you will bring your car onto the highway. That is the best. That is CSMA, carrier sense multiple access. You will sense the channel and then you will transmit the data. Okay, that means sense before you transmit or listen before you talk. That is CSMA. So that is the best. Okay, so these are just for question point of view, I'm telling you Aloha, slotted Aloha questions have been kept, but CSMA is good protocol. Okay, we will study numericals and all from this also, and obviously Aloha, slotted Aloha also have numericals. We will study them also. So the basic scenario now I have cleared you. What is Aloha, what is slotted Aloha, what is CSMA. Okay, so now we can start properly. You can take the snapshot or something so that you can remember this. And now we are going to start the pure Aloha. So what pure Aloha is saying, it was invented in 1970s by in University of Hawaii. Originally it was developed for wireless LAN, but it can be used for any type of media, and an assumption is that station will send fixed and equal size frames. Okay, and there is no condition. No condition. Whenever station want to send data, it can send. Okay, so hence collision chances are very high. You can write down this point. Collision chances are very high. Collision chances are high. Okay, so now since collision chances are high and there is no guarantee that whether the frame which has been sent will be received by receiver or not, there is no guarantee na. Sender will be in dilemma that I have sent the frame. It may have been the case that receiver has received it properly, or it may be the case that because of collision and something like that it has not been received by receiver. Sender is in dilemma. So how he will remove his dilemma? He will expect acknowledgement from the receiver. That is important point. Okay, so in pure aloha, acknowledgements are sent by receiver to the sender, so that sender removes his dilemma that everything has been received by receiver properly or not. So please write this point. So hence sender after sending data will wait for ACK from receiver. Hence sender after sending data will wait for ACK from receiver. And sender after sending data will wait for ACK from receiver. Okay, now till what time sender should wait? That is timeout. This timeout is generally 2 into TP, that is round trip time. Okay, so you can write it. So sender will wait for ACK for 2 TP time. Sender will wait for ACK for 2 TP time. For 2 TP time, that is round trip time. For 2 TP time, that is round trip time. 2 into TP, like this. For 2 TP time, that is RTT, round trip time. Okay, yes. So after timeout, for example, if after 2 TP time station has not received the acknowledgement, or sender has not received the acknowledgement, what should it do? So that means after timeout station will again send the data. That is so obvious. Now something will come into the picture. You might argue with me, sir, when there is no procedure, there is nothing, then why we are studying aloha? You should say simply that send the data, that's it. Okay, so what is the so why we are studying this protocol? Okay, so let me tell you that thing also. So now actual protocol will come into the picture. Till now it was nothing, it was saying like that only, where if station has sent data, you can send it, that's it. This was your normal aloha, what it was saying. Now what I'm going to tell you is, if collision occurred, or rather I should say timeout occurred, okay, after 2 TP time sender has not received the acknowledgement, now what should it do? Now aloha will come into the picture. Take snapshot, I will jump to the next slide and I will tell you those things also.
Done, sir.
Okay, yeah, so after timeout, okay, after timeout, okay, that means what, station has not received acknowledgement, then obviously station will try to send data again. For example, see this is A, B, C and D. For example, B and C, they tried to access the channel simultaneously, or B and C want to send data at the same time. So obviously they will do it, because the law is not stopping anybody. As soon as you want to send data, you can send it. So now B and C both try to send data. So B will send data because it is signal, na? So signal will travel onto the line everywhere, and C will also send the data. Signal it will travel everywhere, so collision will occur obviously. So now because they will wait for timeout, so their 2 TP time will be the same. Now, for example, at 10 a.m., both started sending data. Okay, so now 2 TP time is say 1 hour. So after 1 hour, so their 1 hour will be same also, na? 2 TP time will be same, na? They will wait for same time, na? At 10 a.m. they started, and 2 TP time is say 1 hour. So at 11 a.m. both will try to send data again. So again collision will occur, or again 2 TP time, timeout will expire. At 12 a.m. they will send the data again, or say 12 p.m. they will start sending again, collision. 1 p.m. collision, 2 p.m. collision. So nobody will be able to send data properly. Are you getting it? So now aloha will come into the picture. So after timeout, if station keep on sending data again and again, or rather they will try simultaneously also, na? Because if they try to access the shared channel at the same time, then timeout will occur at the same time. So they will again try to send the data, and there will then again collision will occur, and so on. So effectively nobody will be able to send data properly. So now there will be two important points that will come into the picture. So first write down this point. After timeout, station will again send data. After timeout, station will again send data. Station will again send data, but again timeout will occur. Okay, after timeout, station will again send data, but again timeout will occur because it might be the case that two or more stations try to access the channel simultaneously. Because it might be the case that two or more station tries to access the channel simultaneously. Okay. So all these stations. So for all these station, timeout will be same. So for all these stations, timeout will be same. So for all these stations, timeout will be same. Hence, no station can effectively send the data. Hence, no station can effectively send the data. Okay, no stations can effectively send the data. Okay, so now two points will come into our mind. The very first point should be that station should not send frame immediately after timeout. Okay, no immediate sending of frame after timeout. That is very obvious, because if timeout has occurred, then it will immediately send the data, then again it will do collision and so on. So like this. Okay, so nobody will be able to send data. So basic first point should be, write down, first point should be station must not send frame immediately after timeout. Okay, station must not send frame immediately after timeout. Not send immediately after timeout. Station must not send frame immediately after timeout. Second, number of attempts should be fixed. For example, it is not like that A send the data, collision occur, then again it send data, collision occur, again it send data, collision occur. So it should have a fixed number of attempts. It should not keep on sending data again and again. Okay, because it will unnecessarily collide and so on. So what should be that? So number of attempts should be fixed. Number of attempts should be fixed. For example, generally in every implementation for Aloha, 15 attempts are fixed. So station will not send data more than 15 times. That means 15 tries. You can simply say like that, 15 try. It will try to send the frame 15 times. Maximum 15 times, not more than that. Okay, so number of attempts must be fixed. Number of attempts must be fixed. Okay, like 15. Okay. Yes. So now take snapshot. I will jump to the next slide. Done.
Done, sir.
Okay. So now in first point I have told you that station must not send frame immediately. So how much it should wait? Okay, we have set this point roughly now. So how much it should wait? It should wait for some random amount of time that is known as back off time or TB time. On this gate has asked many questions, so we will study that topic properly. So please write down, because station must not send frame immediately after timeout. Because station must not send frame immediately after timeout. Okay, because station must not send frame immediately after timeout, so it must wait for random amount of time. So it must wait for random amount of time. So it must wait for random amount of time, which is known as back of time. Okay, so it must wait for random amount of time, which is known as back of time. Which is known as back of time. Yes. So what is the value of back of time? Back of time can be say TT or TP or 2TP, random amount of time. Now, so we should multiply it some by random number. So we should say TT, TP or 2TP multiplied by some random number R. Okay, so how to calculate this R? Don't worry, we will tell you these things also. So back of time should be either TT or TP or 2TP multiplied by R. Okay, so this should be given question properly, what they are going to consider for back of time. Okay, so for example, if TT is given, you should take it by default TT. Okay, when TP is not given, then how you will take that? If TP is given, then you will take it as TP only. TT is not given, then how you will take it? That is the simplest way to think about it. Okay, and this is known as, more precisely, we will say it as T slot time. Okay, so actually TB formula is, TB is r multiplied by t slot. Now this t slot or t slot can be, or time slot can be tt, tp or 2tp, depending upon the question, depending upon the numerical, you can take that. Okay, there is no fixed rule and regulation. Okay,
Yes, sir.
so yeah, so if it is your say first attempt, you will immediately transfer the data, that is for sure. Okay, but for example, if it is so we will call it a 0th attempt. Okay, now if it is your first attempt, that means you send the data at time 0. Okay, for example, at time 0 you send the data, because you will send it at time 0 only, because the moment you think that you should send the data, you will immediately send it. You will not wait for something like that. That is what Aloha is saying. Immediately send the data the moment you think about it. So at t0 you will send it. So that is your 0th attempt. You should think like that. That is your 0th attempt. Now if by chance collision occurred, so then you will get your first attempt. So for first attempt, random number will be from any number from 0 to 2 power n minus 1, 2 power 1 minus 1. So that means random number can be either 0 or 1. Now if at that time also collision occurred, then there will be a second attempt. For second attempt, random number will be 0 to 2 power 2 minus 1. That will be 0, 1, 2 or 3. Okay, and then if it is your third attempt, even if collision occurred, you are very unlucky person, and in second attempt also collision occurred, then your random number will be from 0 to 2 power 3 minus 1, that is 0, 1, 2, 3 up to 7. You can take any random number, and that random number will be multiplied by tt, tp or 2tp, like this and so on. Okay, so and number of attempts are 15. I have told you, na, maximum attempts are 15. So in 15th attempt, what you will take, 0 to 2 power 15 minus 1, that means 0, 1, 2 up to 3, 2, 7, 6, 7. Okay, so it is a very, very large number, 0, 1, 2, 3 up to 3, 2, 7, 6, 7. Okay, so as the number of attempt increases, probability of collision also decreases, na? Because see, if two stations are there, then they will take number from 0 or 1. Collision chances are 1 by 2 probability, na? Like both choose 0 or both choose 1, then there will be collision. Okay, so here also here still again decreases exponentially, it will decrease. Okay, so 1, 2, 0, 1, 2, 3. So 4 choices are there. So both take 0, 0, both take 1, 1, both take 2, 2, both take 3, 3. Then only collision. Otherwise, there will be no collision. Okay, so total 4 into 4, 16 ways will be there. From 16, there are only 4 ways in which collision can take place. So collision chances are 1 by 4. Here 1 by 8, and so now getting it. Okay, let me tell you if you are not getting it. So if for first attempt it is there, so then 0, 0, 0, 1, 1, 0, 1, 1, like this. So this is chances of collision 1 by 4. Are you getting it now? Please let me know. No. Okay, so what type of problem are you facing? Then I will tell in that direction.
No, sir, I did not say anything.
Okay, so okay na, 1 by 4 probability.
Yes, sir, yes, sir.
Okay, good. Okay, if second attempt, then what will be our answer? 0, 1, 2, 3 na. So at first place 4 choices, another place, second place 4 choices, 4 into 4, 16. Total 16 choices are there. From this, what are the favorable choices? That means collision will occur when both take 0, both take 1, both take 2 or both take 3. So 4 by 16, that is 1 by 4 only. Okay, so what is this? 8 by 64. Okay, so here one, okay, no problem. Sorry, here 2 by 4 na, 1 by 2. Sorry for that. There are 2 choices na, for which collision will occur. Are you getting it? See this,
Yes, sir.
0 and 1. So if both take 0 or both take 1, there are 2 choices in which collision can take place. Total choices are 4. So 2 by 4, that is 1 by 2. In next case, 0, 1, 2, 3, 4 possibilities. So 4 into 4, that is 16. Total 16 possibility will be there. Like both take 0, or first take 0, second take 1, or first take 0, second take 2, and so on, like this. So total 16 choices are there. And how many are favorable, or how many are taking collision? 0, 1, 2 and 3. 0, 0, 1, 1, 2, 2, 3, 3. So 4 upon 16, that is 1 by 4. Next, if third attempt, so here 8 choices, here 8 choices. Total 64 choices are there. From these 64 choices, only 8 choices will be favorable. Na? Like both take 0, 0, both take 1, 1, both take 2, 2, both take 3, 3, and so on up to both take 7, 7. So 8 upon 64, that is 1 by 8, and so on. So probability chances of collision are decreasing. Na? Like 1 by 2, then 1 by 4, 1 by 8, and so on. Okay, that's why we have taken this as we call it as exponential back off. Exponential back off means exponentially chances of collision are decreasing. Are you getting it? So we call it as exponential back off because chances of collision are decreasing exponentially. Okay. So I think you have got the logic behind it, and that's it. Okay, so this is all about TB, and now we will try to answer gate questions. Okay, so how they have answered, let me how they have asked the question, let me tell you that. I'm not going into detail of writing the question and so on. I'm just giving you the concept, because if I give you the concept, then you will be able to solve any gate question. Okay, if I solve one particular question, then obviously you will be able to grab that question. What about others? So better is I should tell you, or I should teach you the proper concept. So let me tell you that concept on which the questions have been asked again and again. Take snapshot. I will jump to the next slide.
That's it.
Okay. So for gate exam point of view, we will study only binary exponential back of time. Binary exponential back of time. Okay. So we will study this algorithm for gate point of view. Binary means we will talk only about two stations. So in actual Aloha, there might be n stations, and all these n stations might try to send data at the same time. Okay, but their calculation will be very high, and that is out of scope of gate. So we will consider that case when only two stations try to send data at the same time. Okay, 3 or 4 station we will not consider. We will consider only two stations want to send data at the same time. That's why we are calling it as binary. And why we are calling it as exponential? I have just told you, exponential because chances of collision are decreasing exponentially. Okay, back of time. Okay, now let me tell you these things. Okay, so for example, I will say this is station A and this is station B. Okay, so both try to send data at the same time. Obviously collision will occur. Like it will send data here, it will send data here. So obviously collision will occur at the first place. Okay, so in 0th attempt, collision occurs. Okay, 0th attempt. That means why I am calling it as 0th attempt, because the moment he think about sending data, it will send it. That's it. That's why we're calling it as 0th attempt. We are not calling it as first attempt. First attempt means you have attempted something. We are not saying like that. Okay, the moment it has the data, it will send it. So we are considering it as 0th attempt. Okay, 0th attempt, collision. Now both will try to send data at the same time. Okay, so both right, so collision occurred. Now TB will come into the picture, back of time will come into the picture. So first attempt. For first attempt, random number will be between 0 to 2 power 1 minus 1, that is 0 and 1. Okay, two numbers are there. So now I will write the possibilities A and B. Either they will take both zeros, 0 1 1 0 or 1 1. If both take zeros, then obviously collision will occur. That means immediately they will send the data. After timeout, immediately they will send the data. Collision, because after timeout, both send immediately. Both send immediately. How I have used the word immediately? Because this is talking about random numbers. I'm talking about random number. Random number is 0. So R into TP time or R into TT time you are waiting, or even R into 2 TP time, whatever may be the case, whatever they will give, you have to take it. So if R is 0, then obviously you will wait for 0 amount of time. That means immediately send the data. That's why I have told you, when A and B both are 0, then collision will occur, because after timeout both send data immediately. Okay, they will send data, collision will occur. Okay, when A takes 0, B take 1, then what I will say, please see the terminology. This terminology will be asked in gate, or they will say this in gate questions. They will say, since A has taken 0 random number and B has taken 1, so B will have to wait. B will have to wait for TP, TT or 2TP depending on the question. But A will not wait. A will immediately send the frame. So who wins the first back off? A wins the first back off. So I will write here, A wins the first back off. Are you getting it? A wins the first back off means, because here A win, because A will send the data, we have to wait. Since we have to wait, so obviously A win the first back off. Next, A1 B0, what you will say? B wins the first back off. B wins the first back off. Why we are calling it as first back off? Because it is the first attempt. Okay, and 1-1 means again collision, because after TP or TT or 2TP both send data. Okay, because our random number is 1 na, so 1 into TP is TP, or 1 into TT is TT only, or 1 into 2TP 2TP only. So after TP or TT or 2TP both send the data again, so obviously collision will occur. Okay, so yeah, so now they will ask what is the probability that A wins the first back off. See the question is, what is the probability that A wins the first back off? What you will say? 1/4. So simple, because A wins the first back off, total are 4. From 4 there is only one favorable choice. Okay, next, what is the probability that B wins the first back off? What is probability that B wins the first back off? Again you will say 1/4. That is for sure, because B wins the first back off is only one favorable outcome. Okay, yes. And the last question is, what is the probability of collision? What is probability of collision? So collision chances are 2 na, so I will say 2/4, that is 1/2. These type of question will be asked in GATE. Take the snapshot, then I will extend this condition to other ways. Take snapshot. Done?
Yes, sir.
Okay, so now I will assume that so in GATE question they will ask this type of question only. So this thing we have done. Now they will say, assume, question I am saying, assume A wins the first back off. Assume A wins the first back off. That means what? A have taken random number 0 and B has taken random number 1. So that's why we are saying A wins the first back off. Okay, so directly and indirectly, now what this means? A wins the first back off means A, this means what? A, let me write it, means A has successfully sent its first frame. Whatever first frame it was sending, to whosoever it was sending, it hardly matters. He has successfully sent its first frame. That is the basic meaning. Assume A wins the first back off means A has successfully sent its first frame, but B has still, but B still need to send its first frame. B still need to send its first frame. So now what is the situation? Situation is, this is A and this is B. A has successfully sent its first frame. Now A is sending its second frame, but B still tries to send its first frame only. So B is at 1, but A is at second frame. I think it's clear to everybody, na? Please tell me some if there is any doubt.
No, sir. Clear, sir.
Okay. So now in the question they will say, assume A wins the first back off, but when it tries to send frame again, then collision occur. They will say in question, assume A wins the first back off. Okay.
It's a
So this
dictation,
meaning,
sir. Write it down. No, no.
please come again.
Is it a dictation or I need to write it down, sir? No, no.
No. I'm just saying, assume A wins the first back off. Okay. Assume A wins the first back off, and when it tries to send data again, then collision occurs. Let me write it. And when it tries to send frame again, then collision occurs. Then collision occurred. Okay, and they will say probability that A wins the second back off. What is the probability that A wins second back off? Okay, So assume A wins the first back off. This here I have explained you properly. This is the meaning. Okay, and now I have said I have extended the question that when it tries to send the frame again, then collision occurred. What is the probability that A wins the second back off? Okay, so now let me try to answer this question. So situation, I think you have got it. Proper detailed knowledge I have given you that A and B tries to send data at the same time. Collision occurred. Then first attempt come into the picture. So are you getting it now? A and B tries to send data at the same time. Zeroth attempt, collision occur. First attempt come into the picture, and then I have said that A wins the first back off. Okay, that means A chooses random number 0 and B chooses random number 1. Since it was first attempt, so random number will be from 0 to 2 power 1 minus 1, 2 power 1 minus 1. It will be 0 and 1 only. Random number will be either 0 or 1. So I have given you all the possibility for A and B. So when 0 0 1 1 collision, 0 1 means A win the first back off, 1 0 means B win the first back off. So like this we have solved the question, and I have extended now this same question, and now I am saying that assume A wins the first back off. Everything is given like this, and now they are saying that A wins the first back off. That means A successfully sent the first frame, but B need to send its first frame. B is at first frame only, A is sending the second frame. And now what they are saying, and when it tries to send frame again, collision occur. So that means when A tries to send the second frame, then collision occur. Then with which collision occurred? B first frame and A second frame both collide. What they are saying is like this only. Okay, so when it tries to send frame again, then collision occur. So what is the probability that A wins the second back off? Now they are saying that still again A has win the first back off. Now they are saying what is the probability that A again win the back off, or rather A win the second back off? What is the probability? So now let me tell you this thing. See this, when A tries to send the second frame and B tried to send the first frame, collision has occurred. Now please tell me the attempt number. So A attempt will be only first attempt, because it was the 0th attempt for the second frame at which collision occurred. And what about my B? Second attempt. Please try to focus here. Why B second attempt? Because B first attempt has been done already. Okay, at 0th attempt was this. Both tried to send the first frame, collision occur. First attempt was when they chosen the random numbers. So A has chosen random number 0, B has chosen the random number 1. So after A has sent the same frame successfully, and when A tried to send the second frame, then collision occur. So for B there it will be the second attempt. Now first attempt is over. Now B is having the second attempt, but A is at first attempt only. Why? Because for second frame it is the first attempt. For B it is the second attempt. Please let me know if anybody is facing any difficulty here. Why for A it is first attempt and why for B it is second attempt? Any doubt?
No, sir, understood.
Okay, now it's good. So now since A is first attempt, what will be the random number? 0 and 1. For B second attempt means 0 to 2 power, random number will be 0 to 2 power 2 minus 1. That means either 0, 1, 2 or 3. Okay, yeah. So now we will try to establish the relationship. Now it is very easy. So A and B. So A random number is either 0 or 1, but B random number is 0, 1, 2, 3. So with 0 you will write everything 0, 0, 0, 1, 0, 2, 0, 3. Now with 1, 1, 0, 1, 1, 1, 2, 1, 3. Okay, so now see this 0, 0 means collision. Okay, 0, 1 means B wins the first back off. So B wins the second back off now. For B we have second back off now. Oops, sorry.
Collision
What I am doing? Collision. This is the collision. Now here A wins the A win, na? Because A is 0, B is 1. So obviously A will send immediately, but B has to wait. So A win, na? Here again A win. Here again A win. Here B win. Here collision. Here A win. And here A win. Please let me know any doubt.
No, sir, understood.
Okay, so what is the probability that A wins the second back off? 1, 2, 3, 4, 5. 5 favorable outcome from total 8. So A wins the second back off. A wins the second back off. That is 5 by 8. B wins the second back off. B wins where? 1. Yeah, 1 by 8. And collision?
2 by 8.
2 by 8.
Yes, sir.
So isn't it, see, it is not favorable, na? Like A wins the first back off, then probability that A wins the second back off, that is 5 by 8. Already A has win the game. Now still again I am favoring A only. I am not giving favor to B. B win is only 1 by 8. Okay, but A wins is 5 by 8. Collision chances are 2 by 8. Now assume that A wins again. A win the second back off. Now assume A win the second back off. So now what should be the case? A will send the third packet. B is at only first packet. Now let me tell you that thing also. Take snapshot. I will jump to the next slide. This question I've been asking it by the way. Same to same question. A win the first back off probability 5 by 8. Same question I've been asking it. But now I am extended it one step ahead so that they might ask another question also. Let me do it one more step again. Take snapshot. I will jump to the next slide. Done?
Yes, sir.
Okay. So now they will say A wins the third back off. Sorry, second back off. Assume A wins the second back off. Okay. So now what is the probability that A will win the third back off? Probability that A wins the third back off. That is very easy now. See, so what will be our scenario now? A has win the second back off. So A and B, two packets already A has sent. Now it is the third packet which A is sending, and B is only at its first packet, and here collision occurred. So 0th attempt collision. Now for A it will be the first attempt. For A it will be the first attempt, but for B it will be the third attempt. So random number will be either 0 or 1. Random number will be from 0 to 2 power 3 minus 1. That is 0, 1, 2, 3 up to 7. So let me build the table now. Okay. So how table will look like? So A will take value from 0 or 1 only, but B can take value from 0 to 7. So 0, 0, 0, 1, 0, 2, 0, 3, 0, 4, 0, 5, 0, 6, 0, 7. Let me copy it out. 1, 1, 1, 1, 1, 1, 1, 1. Total 16 choices. Here,
Yeah.
collision. A win. A, A,
All
A,
the way.
A, A, and A. Here, B win. Here, collision. A, A. Let me copy it out. Okay, so everywhere A, only one time B, no? So what is the probability that A wins the third back off? So it will be probability that A wins the third back off. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. 13 upon 16. Probability that B wins the third back off 1 by 16. Probability of collision. Collision chances are 2 by 16. That is 1 by 8. So are you getting it now?
Yes, sir.
Probability
Yes.
of collision 1 by 8. Previously collision 1 by 4, and at the first attempt probability of collision was 1 by 2. So collision chances are decreasing exponentially. That's why we call it as exponential back off. And why we are calling it as binary? Because we are talking about only two stations. We are not taking third station into the picture. It will be very mathematical and it will not be asking it. Don't worry about it. Okay. And now see this another beautiful point, that if A wins the first back off, then probability that A wins the second back off is more. Then probability that A wins the third back off is even more, and so on. It is increasing. Okay, this is known as capture effect. Let me tell you that thing. Take snapshot. I will jump to the next slide.
Done, sir.
Okay, capture effect. Capture effect means if A wins the first back off, if A wins the first back off, then chances of winning second back off is more, and chances of winning, this is winning, I'm writing runningly, chances of winning second back off is more, and chances of winning third back off is even more, and chances of winning third back off is even more. So just like that, if A wins, then he will win again. Then again he will win again, and so on. That is known as capture effect. And how this term came? This term came from gambling. So the persons who do gambling, so if you do gambling for the first time, then the other person will try that, he will make sure he will make these kind of combinations and all, that you win first time, you win second time, you win third time, and then you will try to increase your bet more and more and more. And the moment you pick lot of money, and here you will lose the game, and everything come back to the person who was arranging that kind of things. That's why everybody say that gambling is bad, just because of this capture effect. They will try to capture your attention, and then the moment they capture your attention, you will lose the game. Okay, from that this capture effect term has come into the picture. Okay, so I hope you have got the point. So this is all about your back of time. Okay, so and exponential, why we are calling it as exponential? Because exponentially probability is decreasing, binary because only two stations, and probability that A wins the first back off is more than B, second back off is even more, third back off is even more, and so on. It will keep on increasing. Okay, that is by capture effect. So this is all about your back of time. Yes, so now everything is clear. So you can take snapshot of this. If you have any doubt, you can ask me. Otherwise, we will jump to the next topic now. I mean, we are in Aloha only. So now we will study the next thing. Yes, so I think it's okay. So now I will make a you can say a flow chart that will clear every doubt, whatever doubt is in our mind. Summary is, now we are going to write the summary of Aloha. So initially, how this algorithm look like? Start. Okay, we have started the procedure. K is equal to 0. That means it's your 0th attempt. And then what you will say? Send the frame. That means this is Aloha, na? The moment it come to your mind that you will send the frame, you will immediately send it. There is no condition here. You will start. You will say your attempt is 0th. You will say send the frame. That's it. This is Aloha. Okay, then wait for timeout. After sending frame, what you will do? Wait for timeout. Okay, this timeout is generally 2 into TP. Wait for timeout, that is 2 into TP. Now, if you say ACK arrived or ACK received, this will be in diamond box now, because in flowchart you have studied that decision is done by diamond box. ACK received, if it is yes, you will say success. Everything is fit and fine, no need to do any kind of thing. Aloha is over. Okay, let me write it properly. Success. Okay, we have got the success now. If acknowledgement come, if acknowledgement does not come into the picture, no, then attempt will increase. K is equal to K plus 1. Like we have said, now first attempt, second attempt, third attempt, and so on. K is equal to 1. Now you will say if K is greater than K max is generally 15. I have told you. Okay, so this is a decision kind of thing. We will make a diamond here. K is greater than K max. Yes, you will abort your transmission. You will say Aloha over. I was not able to send the data. That's it. You will abort. Otherwise, if it is no, then you will take a random number. Choose random number. Choose random number R between 0 to 2 power K minus 1. For example, if K is 1, initially K was 0, then K is equal to 1, then 0 to 2 power 1 minus 1, that is 0 to 1, 0 or 1. When K is 2, then you will say 0 to 2 power 2 minus 1, 0, 1, 2, 3, and so on. We have done this thing just now. So choose a random number R between 0 to 2 power K minus 1. And then you will say wait for TB time. TB time means back of time. TB time is R into T slot. This slot can be given to you in GATE exam, whether it is transmission time, propagation time, 2 into propagation time, and so on. It can give you anything. Let me write it, no problem. T slot can be the TP, TT, 2 into TP. Whatever may be the case, they can give. Okay, and then after waiting, what you will do? You will send the frame. So you come back here, send the frame. Okay. I think you have got it. Now send the frame, wait for timeout, acknowledgement receive success. No, then in K will increase, K is greater than K max, we will abort, otherwise choose a random number R, wait for TB time, send the frame. Wait for TB time, send the frame. This is a loop which we will keep on executing. Okay, yeah. So this is all about the basic terminology in pure Aloha. Now we are going to start the vulnerable. Okay, and one more question. One more question is coming to my mind. So let me see the time. Okay, we have 1 or 2 minutes left. So what should be done? Okay, we will solve one more question. Don't worry. It is a very small question and it is very simple also. We will study that. Take snapshot. I will jump to the next slide.
That's it.
Okay. So what question they are asking is, we have a pure Aloha network. I am writing the keywords only just to save the time. Consider pure Aloha network in which N stations are there. N stations are present. Okay. Probability that exactly one station, send data is dash, assuming each station send data with probability P. Okay. So what they are saying is, consider a pure Aloha network in which N stations are present. Probability that exactly one station send data is dash, assuming each station send data with probability P. Now if each station is sending data with probability P, what is the probability that exactly one station will send the data? How many stations are there? N stations are there. So what will be your answer? If every station, see this. So I will say there are N stations, like station number 1, 2, 3, dot, 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 up to N. I will say probability that station number 1 send the data. Probability station, any station send data is P. So what I want to find, probability that exactly one station sends data, exactly one. So that means only one station send the data, then 2 should not send the data. When station is sending data with probability P, station not sending data will be 1 minus P. Station 3 does not send data, 1 minus P. And so on. Station N does not send the data, 1 minus P. This is one of the case. Second case will be only station 2 wants to send data. Okay, so only station 2 will send the data with probability P. Station 1 will not send the data. Station 3 will not send the data, and so on. Then station number 3. So 1 minus P, 1 minus P. Station number 2 is not sending data, but station 3 is sending data, and so on. Every station is not sending data. Then station number 4. First is not sending data, second is not sending data, third is not sending data, but fourth is sending data, and so on, like this. So how many cases will be there total? How many cases? N cases will be there. First case answer, P into 1 minus P power N minus 1. Are you getting it?
Yes, sir.
And 1 minus P, 1 minus P, N minus 1 times. So 1 minus P power N minus 1 and P multiplied by. Similarly for others also. This is multiplication. Multiplication is commutative and associative. So every case it is like just like that. Total N cases. So these will be added. So NP 1 minus P power N minus 1. So N into P into 1 minus P power N minus 1. This is my answer. This is a gate question. Okay.
Let me not zoom, sir.
Okay. Should I zoom it? Okay. Okay.
Question, sir.
A question. Okay.
Done, sir.
Okay. Now, so that's it. So now one or two topics are left out, like vulnerable time and all. We will study that in the next class. So most probably in the next class, Aloha will be over, slotted Aloha will be over, and most probably we will try to start CSMA also in the next class. Okay. So most probably I should take 3 classes, 3 to 4 classes. In that your data link layer will be over, and most probably your 50% networking will be over in that scenario, and then only 2 layers, major 2 layers are left out, rather only one, that is network layer, that is major layer. Transport, it is not that much important, we will study only TCP and UDP, only 2 protocols, it will not take much time. And then application layer is very simple, we will study only few points, the which points are coming again and again, we will study that only. Okay.
Okay, sir.
Yeah. Okay then, if anybody is having any doubt, you can ask me, otherwise I will stop the class here itself.
No, sir. Thank you.
Okay then, good night, bye bye.